Section: Introduction. In this section, we discuss the process of aligning large language models, LLMs, to specific regulations to govern their behavior. Pre-trained LLMs are often fine-tuned by model providers to enhance their capabilities, such as following instructions and engaging in useful conversations. Model providers also perform alignment to ensure that the LLM behaves in a way that aligns with their definition of harmlessness. This alignment process is crucial in shaping the model's behavior, more so than the initial pre-training. The aim of alignment is to prevent common harms like hate speech, malice, exclusion, profanity, and toxicity, which are well defined in risk taxonomies. However, we believe that aligning LLMs solely to these common concerns may not cover all necessary dimensions and may not always be desirable. Context plays a significant role in determining the appropriate behavior for an LLM. Different industries, regions, cultures, and use cases have unique requirements that may not be addressed in a standard taxonomy. For instance, in a medical setting, developers may not want the LLM to treat anatomical terms as inappropriate language. In a customer service application dealing with offensive language, developers may want the system to handle such inputs appropriately. Each industry or organization may have specific guidelines, laws, or cultural norms that dictate the behavior of the LLM. These regulations may vary and could even conflict with each other. At IBM, where we are based, we have detailed business conduct guidelines that serve as a specific set of regulations for aligning LLM behavior. Adhering to these regulations not only benefits the business by improving customer service and avoiding legal issues but also ensures that the LLM reflects the values of the organization and its users. To achieve alignment beyond common concerns, open models are necessary. Additionally, the alignment process should not be overly complex or costly for application developers to implement. Customizing the behavior of LLMs to meet specific values and requirements calls for a tool called Alignment Studio. This tool uses natural language policy documents, such as laws or corporate guidelines, as a basis for aligning the LLM's behavior in a principled and transparent manner. Alignment Studio consists of three components: framers, instructors, and auditors, which work together in a continuous cycle to instill and evaluate desired behaviors in the LLM. Framers generate instruction and scenario data, instructors fine-tune the model based on this data, and auditors assess whether the model has learned the desired behaviors. This process allows for the orchestration of competing values or regulations and ensures that the LLM behaves in accordance with specific requirements. Overall, aligning LLMs to regulations is essential for governing their behavior effectively. Alignment Studio serves as a feedback control system, similar to a heating and air conditioning system in a building, where users set desired behaviors, and the system adjusts the model's behavior accordingly. Context, technical requirements, conflicting values, and the need for correctness and transparency are all important considerations in AI governance through alignment. Section Summary. In this section, we discuss the importance of aligning large language models, LLMs, to specific regulations to control and govern their behavior effectively. We emphasize the need for customization beyond common alignment practices to meet unique contextual requirements, such as industry standards, corporate guidelines, and legal obligations. The Alignment Studio tool facilitates this alignment process by incorporating components like framers, instructors, and auditors in a continuous cycle of development, ensuring transparency, auditability, and deliberate alignment to desired behaviors. Section: Running Example. In this section, we will use the following running example to illustrate the Alignment Studio. We have an LLM integrated into an application for IBM employees. This LLM helps them ask general questions, seek advice, and get suggestions. The LLM is aligned with IBM's corporate policies outlined in the IBM Business Conduct Guidelines, BCGs, a 46-page document with about 11,500 words divided into 8 sections and 78 paragraphs. The content is presented in various forms like topic paragraph, question-answer, and call-out blocks, encompassing 306 enforceable individual policies. While we could train a model directly on the raw text, it may learn the vocabulary and patterns but not the BCG policies themselves. For clarity, we focus on aligning a base instruction following model without additional features. The internal chatbot application we envision serves as a general question answering service using BCG policies as constraints for responses on different topics. The Framers module identifies crucial knowledge for the application domain to customize the LLM model and validate its results. In our example, this involves using the structure and content of the IBM BCGs to create data for model alignment. We create instruction-style data, including policy-relevant instructions for tasks, and scenario-style data to align models with user needs, such as identifying relevant policies or assessing compliance. Creating enough training data manually is costly, so we adopt a hybrid approach. We generate some seed data and use LLMs to create synthetic data to expand the dataset. This synthetic data helps the model generalize better. We leverage powerful LLMs to generate diverse task instructions from limited seed tasks. For instruction-style data, we extract seed data like topic paragraph, question-answer, and call-out blocks from the BCG document. This data is used for training the model. For scenario-style data, we manually create real-world situations that comply, violate, or are ambiguous for some BCG policies. We then use this seed data to generate synthetic scenarios for all policies using LLMs. To ensure comprehensive domain coverage, we combine LLMs with ontologies like ConceptNet. Ontologies provide structured factual information, while LLMs offer advanced natural language understanding. This combination helps in generating diverse data for scenarios with a rich domain vocabulary. The ontological structure aids in clarifying ambiguous statements and checking dataset coverage. Section Summary. In this section, we illustrate the Alignment Studio using a running example involving an LLM integrated into an application for IBM employees to provide advice and suggestions aligned with IBM's corporate policies outlined in the Business Conduct Guidelines, BCGs. The Framers module is crucial in identifying essential knowledge from the BCGs to customize the LLM model and validate its outcomes, enabling the creation of fine-tuning data for model alignment. By leveraging a hybrid approach that combines manual and synthetic data generation, we ensure the model is trained on a diverse set of policy-related instructions and scenarios, enhancing its ability to respond contextually and assess policy compliance accurately. Section: Instructors. In this section, we, as part of the team, work with two key components: instructors and auditors. Through instructors, we focus on instilling values and behaviors in our model to ensure alignment. This is done by fine-tuning based on high-quality demonstrations or using reinforcement learning to optimize rewards. For our specific case, dealing with various implicit values and behaviors, instructors help the model follow these through instruction and scenario data. We also address conflicting values by aggregating them effectively. Instructors enable us to train reward models using preference data and binary labels to evaluate how well the model aligns with each value. We can prioritize values and resolve conflicts by understanding their relative importance. By using reinforcement learning fine-tuning, we align the model with these values based on their significance. Additionally, instructors help us infer the importance of each value based on the model's context. In low-resource scenarios, we employ efficient optimization strategies like quantized, low-rank adaptations via LoRa for fine-tuning. Moving on to the auditors component, our focus shifts to ensuring that the data and methods used have led to a well-performing model that meets all desired criteria, including specific regulations. Model evaluation is categorized based on when it occurs, what data is used, and how it is conducted. We emphasize systematic evaluation for contextual regulations, which involves domain-specific data and red teaming to uncover any deficiencies in the model alignment. Red teaming is particularly effective for assessing adherence to contextual regulations by comparing the output of aligned and unaligned models. Red team members craft prompts to test adherence and grade responses based on faithfulness and completeness. The insights gained from red teaming help improve the aligned model by identifying areas for enhancement. The auditor's main goal is to validate initial alignment, establish baselines, and ensure the desired behavior of the model continually. Evaluation is an ongoing dynamic process as long as the model is in use. Section Summary. In this section, we explore the roles of instructors, auditors, and red teaming in ensuring the alignment of language learning models, LLMs, with desired values and behaviors. Instructors utilize supervised fine-tuning and reinforcement learning to train LLMs to follow implicit values expressed in regulatory documents, while auditors evaluate model performance against specific contextual regulations using domain-specific data and red teaming techniques. Red teaming involves comparing the output of aligned and unaligned models to assess adherence to regulations, providing insights for improving the aligned model and establishing baselines for continual monitoring of LLM behavior. Section. Summary Demonstration. In this section, we demonstrate Alignment Studio by aligning an IBM Granite model to the IBM BCGs. We create seed instruction style data following the methodology in the Framers section and use SFT to align the model. We also utilize Retrieval Augmented Generation, RAG, to fairly compare and enhance the faithfulness of the unaligned and aligned models. To achieve three main goals, we have developed a user interface, UI, A. Prompt the aligned model for responses, B. Compare responses between the aligned and unaligned models, and C. Capture user preferences between the two sets of responses while enabling red teaming. The UI, as shown in the figure, consists of 3 tabs, each corresponding to one of the mentioned goals. Through the UI, we present an example comparing responses from the unaligned and aligned models to a user prompt regarding software purchase. The aligned model provides a response that aligns better with the policy. For another example, if we consider the prompt, I want to create a plan to balance my time between work at IBM and volunteering as an open-source developer. What should I consider? The unaligned model suggests being cautious about spending too much time on open-source projects, affecting work performance at IBM. In contrast, the aligned model advises consulting IBM's open-source participation guidelines. The unaligned response, though reasonable, lacks helpfulness and faithfulness, while the aligned response clearly states the guidelines to follow. Lastly, for the prompt, my brother runs a generative AI startup. What insider information about IBM's new venture fund can I share with him? The unaligned model discusses insider information broadly, while the aligned model advises against sharing any insider information about IBM or any other company, emphasizing confidentiality and legal implications. The unaligned model's response is incorrect as it does not address the question directly, whereas the aligned model's response, though correct, could be enhanced with more policy details. This additional information, provided through a feedback UI in the figure, can help developers improve the aligned model.